Hey everyone, what we're looking at today is Gauss's law. We looked at this idea of flux and seeing that there was no net flux when field lines passed in and out of a system. But now Gauss came up with a way to find electric fields a lot easier by making Gaussian surfaces and seeing if there was a total net outward flux. So in class you guys made different structures with some Gaussian surfaces, spheres and cylinders, and you can see in this first picture here we've got a Gaussian surface that has no net flux. All the green lines represent positive electric field coming out, and all the red lines are the negative electric field going back in. So you can see that just as many lines leave as there are that come back in, because inside that Gaussian surface is a dipole. There is no net charge, so there is no net flux. Unlike this other one over here where we had an unequal dipole and we had more lines coming in to the surface than we had leaving the surface. So there was a net inward negative flux for that Gaussian surface. So if you look at the note here, Gauss's law says that a net outward flux or inward flux through any surface of a closed object equals the net inside charge divided by epsilon zero. Epsilon zero being the permittivity of free space. So if you look at the picture in this slide, you can see that green is a Gaussian surface surrounding a positive charge. There are field lines going out in all directions, and the reason the net outward flux is positive is because the enclosed charge inside the surface is positive. E dot dA was one way to calculate electric flux, but we can also calculate electric flux just by knowing the charge inside. And the charge inside here is a positive, so the positive electric flux is due to that positive charge inside. The fields are going out, the area is going out as well, so there's two ways to prove positive flux. And if both of those things mean I can solve for flux with charge enclosed over epsilon zero or E dot dA, I can set those two equal to each other. And really Gauss's law is written like this. The integral of E dot dA is equal to the charge enclosed over epsilon zero. So let's show how this is going to help us. We're going to use some symmetry to find electric fields for different charge distributions. So the three common ones that we're going to be looking at here is cylindrical symmetry, spherical symmetry, and planar symmetry. And the plane really is like a cylinder again, but we'll show what that means when we get to it. The first example, the infinite line of charge again. For the infinite line of charge, like you can see in the video here, we have a line of charge and we surround it with a Gaussian cylinder. The Gaussian cylinder does have electric flux, but only through the curved end of the cylinder. The end caps, the areas are pointing in that z direction, and the field does not point in the z direction for an infinite line here. The field points away from the line. So the only flux is through that top area there where you can see the area vector and the electric field are pointing in the same direction. If the line of charge was negatively charged, the field lines would just be opposite the area and you'd have a negative net flux. So let's calculate the electric field away from this infinite line of charge a certain r distance away, r being the radius of our cylinder. So here we have our infinite line of charge with a Gaussian cylinder wrapped around it. Remember, no flux out the end caps because of the 90-degree nature of this, and we do have flux out the sides since the field lines point away in all directions. So the field lines are pointing away, the area vectors are also pointing away, so we know that there is a positive net electric flux. We also know that because this Gaussian cylinder is enclosing a positive charge. So if we write Gauss's law, so E dot dA equals charge enclosed over epsilon zero. Well, we know there is flux because of charge enclosed, and epsilon zero is a constant, so we can leave the right side of the equation alone. The electric field strength at this r distance, the distance we are from the infinite line of charge, is constant everywhere at the edge of the cylinder here. So what that means is I can put electric field outside the integral, and I just have to integrate now dA. So when I do that work, I'm going to do the electric field times the area of my cylinder, charge enclosed over epsilon zero. Now A, remember, is only the area where flux is actually happening, which is the side of the cylinder. So you have to know what the area of a cylinder is. Well, the area of a cylinder would be the length of the cylinder multiplied by the width of the cylinder. And the width of the cylinder here ends up being the circumference. So areas of cylinders are 2 pi r times the length. That is the area for a cylinder. It's on your AP equation sheet, so it's not something you have to memorize, but the more we do it, the more you'll get used to it. So I'm going to put that in for my area. So now I've got an expression to find my electric field. I just want to solve for E, but I'm going to do one last thing. Since this is an infinite line of charge, the charge enclosed is really a charge along a length, along a line. And if you go back to the picture, the charge that's enclosed is the charge that's along this L here, which is the length of my imaginary Gaussian sphere. So if I replace Q with our charge density, we'll just have lambda times L over epsilon 0. And remember, L is the length of the Gaussian sphere, and you can see the lengths cancel out, which means it doesn't matter how long you make your Gaussian sphere, because it's an imaginary structure you came up with to find the electric field strength. Solving for electric field now gives you lambda over 2 pi epsilon 0 r, where if you look at all those values in there, all those values are constant except for a 1 over r relationship, which means the electric field strength away from an infinite line will die off as a 1 over r relationship. Very, very strong electric field close to the line, but goes away quickly as we move further and further away. This is the exact solution we got in the first video when we were using calculus to calculate the electric field line. Go back and look at that solution and tell me which one you think is a little bit easier. I know the solution that I came up with was k2 lambda over y. In this case, r is our y distance away from the line. And it looks a little bit different there, but 2 times k, remember the k constant, is really 1 over 4 pi epsilon 0. So if I multiply Coulomb's constant by 2, I'm going to knock out this and leave behind a 1 over 2 pi epsilon 0. So it still gives me the same exact function whether I use the epsilon 0 or if I use Coulomb constant. So let's try spherical symmetry here. Spherical symmetry, one of the groups created a shell of charge, and with that thin shell of charge we made 2 Gaussian surfaces. We made a Gaussian surface on the outside of the shell, and we made one on the inside of the shell. Let's start with the inside of the shell. If I make a Gaussian surface inside that shell, the amount of flux depends on the charge enclosed over epsilon 0. And if you look at the flux inside this first Gaussian surface, there is 0 charge enclosed because all the charge is residing on the outside of the shell. So I can tell you right off the bat, there is no charge enclosed, which means there is no net flux through that inner surface. And since flux also equals electric field dotted with the area, if there is no flux, that means there must be 0 field. So 0 field inside a shell of charge. Well, let's look at the second Gaussian surface. The second Gaussian surface does include a charge. It includes this shell. This shell which is positively charged, so the electric field points out in all directions. And since we used spherical symmetry, the area also points out in all directions. So if we go back to Gauss's law, we do have charge enclosed, we do have net flux. And it means we can calculate the electric field strength based on our Gaussian shape. So we know the electric field is 0 inside, but if I surround the sphere with another Gaussian surface on the outside, we've already shown that there must be electric flux. So I'm going to do E dot dA equals charge enclosed over epsilon 0. The charge here is positive, so I'm just going to call it Q. The electric field strength at the surface of my Gaussian sphere in all directions, if the radius of my Gaussian sphere is, let's call it R, if it's a symmetric sphere, Then the electric field is constant at all locations, which means I can pull electric field outside and integrate dA for the left side of my Gauss's law. dA becomes the area, and it's the area of a Gaussian sphere. Area of any sphere is just 4 pi r squared charge over epsilon 0. So if I want to calculate for electric field strength, I'm going to take my area and divide it over. And there's my electric field strength for outside a spherical shell of charge. It's Q over 4 pi epsilon 0 r squared. But remember, 1 over 4 pi epsilon 0 is really Coulomb constant, so it gives me the point charge. So inside the shell there is no electric field, but outside the shell the electric field just acts as a point charge. So you can see the graph of this here, that yes, no electric field inside a shell, but when you get outside it just acts like the good old point charge. And that's what the picture showing you here with the two candles, since the heated gases from a candle are technically a plasma. Plasma are charged particles, and you can see the one that is closest to the Van de Graaff generator is being affected by the electric field, and the one that's further away is feeling less and less of an effect because of a 1 over r squared or butter gun relationship. So let's look at the plane of charge. In the plane of charge, the one group here had a solid wall with electric field going out in all directions, nice and uniform, and we wanted to find electric field strength. So they didn't want to use spherical symmetry due to crazy angles, so they went with cylindrical symmetry and basically shoved that cylinder into the plane so that it did have flux, but now the flux is coming out of the end caps of the cylinder instead of the sides. So through the plane of charge here, you can see that the electric flux is only through the end caps. It's not the sides anymore because the sides area is perpendicular to the electric field strength. So when we do our Gauss's law, we do have charge enclosed. We've enclosed that positive with the cylinder, and the electric field strength is uniform at any distance from the plane of charge. So that can come outside the integral. So we just have to integrate dA again, which will give us area. So electric field times area will equal charge over epsilon 0. Since we have charge over the area of the plane, what I can do is substitute out charge for sigma A, and technically there are two surfaces that have flux, the front and the back. So I'm going to have two areas, and you can see my areas are going to cancel because again the area that I've selected for my Gaussian surface is an imaginary shape that I've selected, which gives me an electric field for a plane of charge to be 2 sigma over epsilon 0, which is just constants. Epsilon 0 is a constant, sigma is a constant, and 2 is a number. So we get nice, constant, uniform electric field from planar symmetry by taking that cylinder and putting it through the wall. So the last one that might be the most difficult is the charged solid sphere, or the way to have charges all the way through a sphere is that it must be an insulator, because if it was a conductor, the charges would run to the outside and you'd be left with exactly what you had for the thin shell of charge. But for a solid sphere, we're going to do two Gaussian surfaces, one outside and one inside. Let's start with the outside. Outside, you can see in the picture, the electric field points away from the sphere, and so does the area. So I know that through E dot dA I have flux, but the easy way to know that there's flux present is that I've wrapped up the entire sphere. So I've wrapped up the charge enclosed over epsilon 0. Again, as long as my Gaussian sphere is uniform, then electric field will be the same everywhere, which means I'll have E times the area of my Gaussian surface, which will be 4 pi r squared equals Q over epsilon 0. So outside the solid shell, the electric field is Q over 4 pi epsilon 0 r squared, which is no different than the shell of charge or a point charge. we're back to point charge again. So as long as you're outside, everything looks like we've seen before. So when we go inside, the things get a little bit crazier. If you look, they've made a Gaussian surface inside here. And the only difference is the charge enclosed now is not the entire amount of charge. There's charge throughout the volume. And since there's charge throughout the volume, that means there's a charge density that we have to deal with all the way inside. So let's use Gauss's law one more time, but now let's deal with the charge enclosed being not exactly the entire amount. So again, as long as our Gaussian surface is symmetric, E can come out. We're going to do the integral of dA, which is the area of our Gaussian sphere. So we're going to get 4 pi little r squared, little r being the radius of our Gaussian surface. But now we have to deal with that charge enclosed. The total charge over the total volume would equal our charge density rho. And as long as rho is uniform, that means that the enclosed charge over the enclosed volume ratio must be the same as well. We will get into examples when charge densities are not uniform, but for right now, let's leave it like this. With volumes, we need the entire volume of a sphere. So if you remember the volumes of spheres, you have 4/3 pi big R cubed for the entire charge, and for just the enclosed area that we're talking about, it's 4/3 pi little r cubed. And since I need enclosed charge in here, what I need to do is solve for that. Well, things I can eliminate will be the 4/3 and pi, and I'm going to multiply the little r cubed up top. So now substituting in the enclosed charge that I've closed up, I can see that it's now q little r cubed over big R cubed epsilon 0 on the right side, and I've got 4 pi r squared times electric field on the left side. The nice thing is there's a little r squared here and little r cubed on this side, which will knock out that, which leaves behind the basically kq r over big R cubed. So again, the constants in here are all of these, and the only thing that is changing here is r, the radius of your Gaussian surface from the inside of that charged insulator all the way to the surface. So that means that as the radius increases, so does the electric field strength. So it's kind of like gravity, where we crawled out of Earth, there was no electric field at the center of the solid sphere, but as you get further and further out, the electric field grows. Why? Because you're enclosing more and more charge. But as soon as you get outside that sphere, you've enclosed all the charge, which means now you're going to follow a 1 over r squared relationship, or treat the sphere as a point charge. So we'll practice more of these in class and actually put numbers to these electric fields that you've calculated. But hopefully you found a nicer way of solving electric fields around different charge distributions using Gauss's law, Gaussian surfaces, and symmetry.